So yeah, without further ado, here is Isabel Martos giving us an exciting talk about electrical engineering. Go ahead, Isabel.
Yeah, okay. Hi, everybody. My name is Isabel Martos-Repath, and today's talk, I gave it this super lame title last week because I should have planned better. And, well, I don't know. Puns are just like not my strong suit. But we'll be talking a little bit today about what electrical engineering, or EE, is, and what I do within that discipline, which I refer to as analog design and modeling. So just an outline for today's talk. I'll tell you guys who I am because it's been a bit since I've been back to California. What I'm doing now, which is graduate school, how I got there, what is electrical engineering, what is modeling for circuits, and then we'll conclude, and I put some resources down. If today's talk sounds super interesting to you guys, then there are some resources and you guys can look into them and learn more if you want. Okay, so I graduated from CV in 2014. I joined the robotics club as a freshman, which was way back in 2011. And the game we played was called Logo Motion. And while I was on 589, I did a lot of things. One of the things that I loved the most was that I was a first LEGO League mentor. And I think I know some of you, maybe, I don't know, so maybe the kids that I did FLL with have all graduated at this point. I'm not actually sure. But it was a really great experience and it had a really big impact on me. But on the team itself, I did lots of different things. I worked with design, I helped with welding. There was a year that I helped with pneumatics. And I was also a chairman's presenter. And then because I saw that you guys put it on the Instagram thing, I did win the Dean's List in 2013. But 589 was probably like the coolest thing that I did in high school, and it had a really big impact on my choices for what I wanted to do in college and what I wanted to do, hopefully, with my career. And I thought I would put this map because I thought it would be fun to sort of point out physically where I've gone, as well as education and career-wise. So then from CV, I went to a little tiny school called Harvey Mudd College, which is not very far away from CV. It's actually only 35 miles. It's in a place called Claremont, California. And it's a really tiny school. There's only 800 people there. And the focus is completely on STEM. So you can only major in physics or computer science or chemistry or biology, math, those kind of things. And engineering. So we don't even do mechanical engineering or aerospace engineering. They just call it engineering, and it's multidisciplinary. So what they're trying to do is we cover a lot of disciplines, and we learn about lots of different ways to solve engineering problems and how to look at them from the sort of lens of lots of disciplines and using lots of problem solving tools. Which is, I think, a pretty neat way to teach engineering, and I got a lot out of it, and lots of people that I went to school with are out doing really cool things and working in all sorts of different jobs and industries. And because it's a liberal arts college, you also do lots of humanities work, which is not always typical for somebody that goes to college and majors in STEM. And I think that's something that's really cool and special about Harvey Mudd as well, is that you don't have to do science and math all the time. You also get to learn about, in my case, I took a lot of political science courses, but I had friends that, majored in computer science but had dance concentrations, or people that did languages. And it really, it sort of reminds you to look at the world not just through a really quantitative lens where everything is just numbers and logic and stuff, but I think it sort of adds that interesting dimension to stuff. And while I was there, I did research. I did something called the clinic program, which is at Harvey Mudd what we call the capstone, so the big project that you do when you're a senior. I also interned, and I worked in the machine shop, which is something I was really excited to find that they had coming out of 589's shop. Is, I was like, oh yeah, awesome, I get to go back and do a shop, and I get to learn how to work on the tools that we had in the college machine shop, and I was able to help other students learn how to make different things for their classes and learn how to use all the tools really safely there. And I was still able to volunteer with FLL. So one of my professors and I started a team with some of the kids from like the faculty and the staff at the school, and we would meet on like Tuesday nights in an empty classroom. It was really nice to be able to stay like linked to FIRST, even though I was off of school. So one of the things about going to a small school is that they don't have a lot of students to pick from when they do like promotional photos and videos and things. So this actually came out like 2 weeks ago, and it made me laugh a lot because I've been out of undergrad for 2 years, and they put up this flyer for a program that they're going to be doing at Harvey Mudd, and they had a picture of me from when I was a freshman, and my friend Iyasu, who's actually my roommate in Boston, and he's there in that picture working on an underwater robot. So I thought that was really funny. And you know, if you're like super into being in promotional photos, then I guess maybe a small school is the way to go. And then, so now I go to a place called Northeastern University, and when am I going to finish? Not sure, probably in like 3 to 5 years, because I am now working on getting a PhD. So I actually came to Northeastern originally just to do a master's degree, but I decided that I really liked graduate school, and I decided that I would stick around and do a doctorate, so I'll be starting that in the fall semester. And at Northeastern, I do electrical engineering, or as the university refers to it, I do microsystems, materials, and devices. And what that means is I do like a very physical subdiscipline of electrical engineering, and we'll talk about what that is in a little bit later in the presentation. So I currently, as of from fall 2018 until now, I have been working in a lab called the Analog and Mixed Signal Integrated Circuits Group, and I work for a guy named Professor Marvin Onabacho. And I will be joining a lab called the Advanced Materials and Microsystems Lab, and I'll be working for Professor Sun. And they're sort of connected. We've all been working on a really big project, so I'm not making a huge jump. I'm just switching the person that I guess I directly report to. And as you can see, I went from living in Southern California my whole life, and now I live in Boston, which I have to say is a pretty great city. It is not quite as hot as California, but it is very, very humid at the moment. I think we're actually getting like the tail end of the hurricane that's like hitting North Carolina or something right now, because we've been getting lots of thunderstorms today. And I thought I would throw in a picture. This is me in my lab group, and I wanted to highlight that it's half women, which I think is really cool. So my lab mates and I are from all sorts of different places. I have lab mates from India, I have lab mates from China, I have lab mates from Egypt, and I think my professor is like German and Nigerian. So we're like a super international group, and they're all really cool, brilliant people, and I really like spending time with them. And we're there in front of our, what is not the prettiest building on campus, but it says Northeastern, so we decided it was a good spot to take a group photo. So I apologize for the small font, but I was like, I don't want to break this up anymore, because I thought the visual just got weirder and weirder. So I've made you all a flowchart to just, because part of this talk I wanted to explain, like, what is it like to go from a place like CD, and then, you know, what is grad school? How do you get there? Like, would you even want to get there? So I just sort of wanted to explain like how it worked out for me, just so you to sort of provide the opportunity for you guys to see, like, you know, how would that even work? So basically, I went to Harvey Mudd, as I mentioned, and in my first year, I did research. So I was a summer research student, and I did material science research, even though I'm now an electrical engineer. And then the next year, I did manufacturing engineering research. And these were both on campus, so something that you can do if you decide that you want to major in a STEM field. I'm sure you can also do this in other disciplines, but I can only speak to how it works in the STEM fields, is you can do something called a research experience for undergraduates, or REU, when you go to college. And those are very helpful if you think that you might enjoy going to graduate school, because graduate school really looks at, it's all about research. So it's all about doing more classes and learning more things, but also learning by doing research and like furthering the field and furthering the discipline. And so it's good to get practice for that in undergrad, and it helped me decide that it was something that I liked doing. And so those first 2 years were very helpful for me because I was able to stay on campus and sort of get a feel for what doing research was like. And so even though I was doing them in disciplines other than electrical engineering, I still got a lot out of that. And I got to know 2 professors, and they helped me later on when I was going to graduate school in like picking programs and writing letters of recommendations and things. So I highly recommend doing RUs, and you can find out more about them when you go to college by talking to your professors. And often universities and colleges will also have offices of like undergraduate research or programs for helping you find out how to do these types of things. My junior year in college, though, I decided I wanted to see what it would be like if I went and worked in industry. So I got an internship at Meggitt Control Systems, and I actually worked for one of 589's mentors, Mr. Abrams, and I had a really great time in that role. And I learned a lot about what it was like to be a professional engineer in like the aerospace industry. And I really do like industry a lot and would very much like to return one day. You know, the focuses are different, and the pace is very different from what grad school and research is like. But I think I think I was very fortunate to have the opportunity to try both things. But then when I went back to school that fall and I was a senior, I decided that I was really into electrical engineering because I'd been taking more and more classes on that. And I was working on a big project related to electrical engineering. And so I decided that I wanted to go get a master's degree. So I applied to some programs and decided that I would go to Northeastern. So I moved to Boston. And it was really cool. I was like, oh my gosh, all of a sudden, all of my classes are only electrical engineering. I found an advisor and a project to work on. So I found Professor Onobacho's lab, and I started working on a project for these, they're called nano-neural RFIDs. So we're trying to build wirelessly powered and like things that we can communicate wirelessly that we implant in the brains of mice and study their brain activity. And then now I'm in my second year, and by now I have written a paper, which I am super excited to be presenting next week. I have decided that I'm going to stay on for a PhD. And this past spring, I was also an intern at Bose Corporation, which was super fun and a really cool opportunity to see how consumer electronics works as an industry. Okay, so enough about me. Let's get into, what is electrical engineering? And I mean, like, this is a super, super high level overview because it's a really big field. It's a lot of things. So it's designing circuits, but it can also be like robotics. I have friends that like build underwater robots. I have friends that like work on self-driving cars. You can do power electronics. You can go think about power lines and power grids and how you get electricity to people's cities and homes. So those are just like a couple disciplines, but it's a really big field, which makes it kind of crazy to think about how when you can go to college and you can just major in electrical engineering, because it's like, well, that's a lot of things. But what I do, so I just went ahead and quoted my lab's website, is these words are all super huge, but I thought I would try and break it down, is the design of analog radio frequency and mixed signal integrated circuits. So what does that actually mean? Well, if you've ever seen one of these, this is a PCB, or printed circuit board. So if you ever open up like some piece of electronics at home, or if you look inside the robot, I guess sometimes the boards that we use to do all the powering of the robot sometimes look like this. This is a PCB. An integrated circuit looks like that. It's one of the little tiny like black boxes, or we sometimes call them ICs. Some people kind of refer to them as chips. But those little parts that you see populating a PCB, that's what I mean when I say integrated circuits. And so those are circuits that you then package up and combine to make other circuits that build systems and do all sorts of stuff. So modeling for circuits. This is one of the things that I do, and I thought it would be a fun thing to talk about, since it's something I've been working on a lot this summer and that I'm preparing for to give a talk on. And I was like, yeah, 589, you guys can definitely relate to this. And maybe I thought I'd try and give you an overview of what that is in my world and how that connects to being on a first robotics team. So prototyping, we all know it's super useful. On 589, if you're building a physical prototype, you might be building out of some like 2x4s. Maybe you're using metal, cardboard, tape, all sorts of things to try and build a little model, physical model of the robot or the mechanism that you're trying to build, or just to sort of get an idea of what maybe the field looks like for the year. I count CAD, I think, as a prototype. It's important sometimes for helping you figure out how things fit together. But I sort of grouped it in this category. That was my operating definition. And I count math as a prototype. So, if you are writing down the physics equations or doing the trigonometry to figure out how a part needs to be designed, that's kind of like a prototype, because you're building a model of the behavior of something on the robot. In circuit design, prototyping looks a little bit more like this. So the thing on the right in this picture is, we call it a breadboard. And a breadboard, you can kind of think of it as like Legos for circuits. So it's a little board that has electrical connections set out in a grid. And if you can plug things in a certain way, that helps you build circuits without having to go through the whole process of building a PCB. So, if you've plugged in something wrong, you can just pull it back up. Whereas if I had a printed circuit board, that takes quite a long time to design. It takes money to actually have it fabricated, because you have to send it off to a special factory that makes it for you and then mails it back to you. So a breadboard is an easy way to just plug and play and see how a circuit works. And they're also very common. If you go to college and you major in electrical engineering, or you major in engineering, whatever, you're probably going to run into one of these. They're also good for just quick hobby projects. But as you can see, this one has some integrated circuits. These are little devices that are probably operational amplifiers. I have some resistors in here, and then some other sensors all plugged in, and then the wires are all connecting them in the way that we've designed the circuit. So then this guy from the right, actually, we made it into a more finalized version on this green board, which is technically called a proto board, but it's just sort of a more set version. So this version was actually soldered together so that the pieces can't rattle around, because this whole thing went inside of did it skip my pictures? I just hit the wrong way. It went inside of a rocket. Wow, I'm sorry. I was trying to make that suspenseful, and it turns out I don't know how to work the direction keys on my keyboard, so whoops. Anyway, it went inside a rocket. This was a project that I did while I was at Harvey Mudd, and we had built a bunch of circuits to enable some sensors to work. We were trying to get information on stuff like air quality, so we were measuring carbon monoxide content of the air. We had some temperature sensors, because we were going to mount them all inside this rocket and get cool information about the atmosphere in the part of the desert we were in. So we had this great plan, and we built all these cool circuits that we designed and set them up, and then it crashed. So here's a picture of me and my best friend Lillian looking at our rocket that had crashed into the desert floor. And this actually happened twice. These were two separate rockets. So if you noticed in the last slide, that one had a different paint job than this one. And it's because we managed to crash both our rockets, which is not great when it's your final project and then you have to tell your professors that you weren't able to collect any data because both your rockets crashed into the ground. But regardless, my team and I learned a lot. So as you can see, we're all smiling, even though we're holding our rocket wreckage. And we definitely learned a lot about circuit design and the sort of practical aspect of engineering in that class. So circuit design, prototyping and modeling can also look like math, but instead of just sort of writing physics equations on the board, what that looks like for me is, drawing schematics and using circuit simulators. So these are computer programs that essentially do all of the math and physics for me. So they are running, they are solving equations over and over and over. And so what it allows me to do is take the design for a circuit and simulate what it's going to do in real life over, different periods of time and under different conditions. And that's really important for doing in the design process, because you might have to change things, and it's not going to be possible to do that, especially on an integrated circuit level, if I need to make it every single time. So it's important to do the math before I actually build it and put it put it to work. So this is the title slide, actually, from the talk I'll be giving next week. And so I'm going to give an example of a circuit model, and it's for a device called a magneto-electric antenna. And we have built a model for when we use this device, the magneto-electric antenna, in circuits that do magnetic sensing. So I wanted to give credit to all the people that I work with and the advisors. And when you give academic talks, you have to give all sorts of specifications of like who you worked on. It's really important to give credit to your collaborators. And my email's there, I guess, if you wanted to email me, my academic email address. I know the conference also says it's in Springfield, Massachusetts, but it's going to be virtual, and that's just like a cool pandemic thing that's different now in academia than it is normally. So I've actually, I think that 589ers are brilliant and awesome, and that you guys can totally handle some of my actual conference slides. So I have mostly taken the slides I will be using in my talk, but with like modifications and things. And I was like, yeah, let's do it. Let's talk about magneto-electric antennas. So what they are you guys able to see my pointer? I hope so. So this is a CAD model of what a magneto-electric antenna looks like. It's really tiny. We're talking about sub-millimeter size. So like 1/4 of a millimeter is like one of these dimensions. That's actually like the largest dimension. So they are really, really tiny. And this magneto-electric antenna gets incorporated with other circuitry. And so in our case, we are using it to build magnetic field sensors. And these antennas are really good at sensing really, really, really weak, so weak, like low magnitude magnetic fields. So if you wanted specific units, picotesla to millitesla. Picotesla is 10 to the negative 12th Tesla. Tesla is a way of measuring how strong a magnetic field is. And millitesla, milli is the prefix for 10 to the negative 3rd. So these are very small magnetic fields. And then also low frequency. So that's also an important criteria for the fields that we're trying to sense. And that makes them really useful for if I wanted to build a magnetometer, but it also makes it really useful for things like if I want to sense brain activity, because it turns out that neurons, when they fire, emit really weak magnetic fields, and they also happen to be pretty low frequency content, so like under kilohertz. So these magneto-electric antennas we're hoping to design a device that we could put on the surface of a rat's brain and then look at the activity of neurons that are happening, that are like firing in the brain, and give us a sort of a more localized, a more descriptive picture of what happens in the brain, as opposed to like a non-invasive method like EEG, so electroencephalography, or MEG, which is magnetoencephalography. So kind of like if you ever have been to the doctor and you get an MRI or an EEG, that gives you a really like large picture, so large scale picture. This would help us get a more detailed picture. So hopefully that would be useful to somebody like a neuroscientist, or people that are trying to treat sort of brain disorders, like maybe like epilepsy, things like that. So that's the application. But math. Okay, so don't freak out. These are just trig equations. So and it's nice because I like looking at it because I'm like, oh my gosh, it's just trig equations. Even though like we're all in I'm all the way up in grad school. Like all I have to worry about is multiplying cosines. So kind of break out those trig identities. So what happens is this device, this magneto-electric antenna, it gets powered in a way with a voltage, and in my discipline we'll refer to that as the carrier signal, so V of t. And that device is going to be sensing some magnetic field, and we call that B of t. So those are both just we cosines because they're like the signals, they're signals that have like different content, and they have magnitudes and frequencies and things. And so what happens is the ME antenna is getting powered and it's sensing some magnetic field, and the way it responds is it emits a voltage, and this voltage has a pattern that takes the form of this equation. So it turns out that it behaves as if we're just taking these two signals and the equations that describe them and multiplying them together. And this has to do with the sort of the material properties on the sort of highest level way of describing it. But we get this like neat equation where we just multiply these two cosine signals, and what happens when you multiply cosines? You can expand them, you get more cosines. So there's a lot of cosines here, but what we're interested in is these omegas. So an omega is representing a frequency, and so there will be a number associated with it. And normally when we have like XY plots, you know, we expect on the x-axis to like have like time, for example. And it's pretty common in engineering that you could also put, instead of time on the x-axis, you put frequency. So what this means is if I have different frequencies, like if this was 1 and this was 2, then I would see a spike at 1, and I would see a spike at 3, and I would see a spike at -1. And experimentally, when I set up my whole experimental setup, and I have all my equipment, and I have a machine that does collect some data, and when I process it, it'll give me a spike. But again, we have this like frequency content on the x-axis, as we call it. But what happens is, yeah, I have some stuff at my carrier frequency, omega c, and I have some information at these other two frequencies, which happen to be the sum and the difference of what's inside each of these cosine expressions. So if anybody has questions, you feel free to jump in. I hope that math was like somewhat clear. But anyway, this is what happens in our experiments. I get these funny looking graphs and I get like 3 big spikes. And this is the information that I'm curious about in my circuit and that the little magnetoelectric antenna device is sensing. And so when I'm designing a circuit, I want to take this magnetoelectric antenna and I need to design some other circuits, to some other parts of the circuit. You know, I'm going to need to attach parts that will help me power it. I'm going to need to attach other components to help me like deliver the information that it's sensing. And so what I need to do is I need to make a schematic. I need to draw out all of these parts, and I need something that is going to represent the antenna. So there is a model for that, and it's called the Modified Butterworth Van Dyke model, or MBVD model. And this is a pretty like generic model in the circuits community for representing things that resonate, that oscillate. And so we have like, you know, some resistors, some capacitors, and an inductor, hence the talk title. And this is supposed to be a circuit level representation of that antenna. But what happens is if I put this into one of my circuit simulators and I try and design a circuit with it, it doesn't behave exactly the way that it does in the real world, so in experiments. And that's an issue, right? Because I want to design circuits and I want to be able to trust the math that the model is giving me. I want to trust that it's going to do the same thing in the real world as it does in my design. So what we need to do is modify the model to reflect what the device does in the real world. And that way I can trust the designs that I make and simulate before I actually go and build them. And so what we did is we added this little red block. So this is an inductor, but as you can see, it's got this arrow through it. And in circuits, that means that the value is not fixed, that the value of that component can change. And so what it is it's a variable inductance, and its value is controlled by the magnetic field that the device is being exposed to, that B of T from before. So we went in and we wrote some code, and the code is pretty much just the mathematical equation for inductance, which is a quantity in circuits, just like resistance and capacitance, which you're more likely to talk about in your physics classes. Inductance is just another component. And the values, so we just have some code in a language called Verilog A, which is a hardware description language because it's describing a piece of circuit hardware. And the equations that we wrote out allow the value to change when it's dictated by this value. And what that happens when we update our circuit model is when we run simulations, they now behave like we see in experiments. So we see those 3 spikes again, which is, one spike is our carrier signal, our power, and then the other 2 have the information that we're interested in, our modulation components. So this is great because now we can go and design circuits with these devices, with these magnetoelectric antennas, and we can expect that what they do in the simulator is more close to what they're going to do if we actually build that device, that circuit in real life. And I put an asterisk here because models aren't perfect. So for example, in ours, below a certain magnitude of magnetic field, we stop performing within 6% error. So the model is only valid for a certain range of conditions that the device, that the magnetoelectric antenna might be exposed to. And I think that this is very true of things in most cases, like in 589, if you are doing mathematical modeling and you're trying to model how the robot drives across the field, things like friction, things like wheels slipping on carpet, etc. There's too many things to include in a model, and so at some point you have to go, I'm going to model it for this set of conditions, and I'm going to make these assumptions about what the robot, or in my case the magnetoelectric antenna, is going to experience. And it's going to give me a good enough picture of what might happen in real life that I can then use that information to make engineering decisions before I build. And that's really what we want models for. So in conclusion, prototypes and models, even when they're not physical, even when they're based in math or in simulators, are really helpful parts of the design process. In 589, it's helpful for before you go and spend a whole bunch of time and money and effort on building a robot. It's very helpful to have like a rough idea of what you think something is going to do. And in electrical engineering, this is super helpful for us because we need to prove that a circuit design is going to be a good choice for us to then go and build. So when you build integrated circuits, a square millimeter of integrated circuit runs about $10,000, and you have to ship them off to foundries, and there's not very many of them that can actually make these for us. So our professors are like, we want to see really good results before we go ahead and spend all of the time and money that's coming from funding agencies like the National Science Foundation and the National Institutes of Health. They want to make sure that we are really sure about our designs before we go and build them. And electrical engineering, again, really big, cool field. Analog circuit design is one part, but if you go to college and you study EE, you're going to do analog circuit design because it's really the basis for a lot of the other parts of EE. You're going to need to understand how circuits work because they're going to be, in the robots that you might build. They're going to be, in the power grids that you design for cities and towns. And then just on sort of a life note, one of the things that I have learned along the way and that I really learned as part of my time on 589 is that asking questions and then trying new things, even if you're not sure that you're going to be able, you're going to be good at them and you're kind of scared to try them as a result. You're going to learn when you do those things, and that those things can lead to new opportunities. So when I was in high school, I, was pretty sure that I was just going to go to college and get a bachelor's degree in engineering. But I went and tried all sorts of new disciplines, and I tried electrical engineering, and then that led to a master's program, and that has led to a PhD, which is what I'm doing now. So, if any of this sounded cool, if you weren't freaked out by all the cosines and all of the weird looking diagrams of mysterious components, and you want to learn more about electrical engineering, well, first take lots of math and science classes because that'll help you a lot in college. talk to your mentors. Some of them are electrical engineers. And I didn't add this on the slide, but you can also reach out to me if you're like, want to learn more about what going to school for electrical engineering is like. And there's lots of like free tools that are like, you don't even need like special hardware and stuff to like go and learn more about electrical engineering. Two of my favorites are the websites SparkFun and All About Circuits. All About Circuits is kind of like, it's like a really well written, almost like intro textbook. And it'll just give you like as much information as you want about how things work in circuits. And SparkFun is filled with like all sorts of really great tutorials about how to use different electrical engineering tools. If you want to learn how to design PCBs, Eagle and KiCad are two very commonly used PCB design tools, and they're both like free and open source. Or KiCad is open source. Eagle is free for like personal use and stuff. When I was working at Bose, Eagle is what we used on my team. So these are both tools that are used in industry and that you could learn if you wanted to start learning about how to make your own circuits. And then Arduino and Raspberry Pi are great ways to learn about how to interface electrical engineering circuit design with like software, things like that. So if you guys, thank you so much for patiently listening to me talk about math, and go 589. And if you have any questions, go ahead. Should I stop sharing? Hey.
Maybe start with your mom's question. When you were an undergrad, I think you built a computer from an Arduino. Could you speak to that experience?
So I didn't build a computer, and it wasn't from an Arduino, but thanks, Mom. So I didn't put a picture of it in my presentation, but we built a tool called an oscilloscope, which is a tool that you can use to measure electrical signals in circuits. And we used a Raspberry Pi and some other hardware. And Raspberry Pi is kind of like a $40 computer that doesn't come with a screen, but that you can like put code into and use to drive interesting circuits. Yeah. Ooh. Okay, so Heather wants to know how I feel 589 prepared me for a STEM undergraduate degree, and if not, what else might high school students do to better prepare, if anything. So I think 589, some of the most valuable lessons that I learned from being on the robotics team were about working on technical projects with other people. And so I think going into a STEM undergraduate degree, I was already like better prepared than a lot of my classmates were for working on like lab projects and group projects and collaborating on math homework and physics homework and everything. As far as like practical skills, engineering is such a big discipline that there's like so many things that you're just like not going to know going in. So, for example, the breadboards that I talked about, I had never used one going into school, but it was okay because I was prepared from 589 to be like, okay, here's a difficult problem that I don't know anything about, but I know how to work with other people to learn the skills for us to solve this problem, and then for me to learn how to like use this new tool or something. And then as far as like what can high school students do to prepare for a STEM undergrad degree, take science and math classes, stay involved with 589, read lots, ask lots of questions, and stick with it.
Could you actually bring up your slides again and go back to the one with the math?
Yeah.
Because I may have missed it in your explanation, but with those peaks, did you know that's what you were looking for? Or is that just what the math model told you should be looking for?
This one?
Yeah.
Yeah, so this is experimental data. And since I knew the conditions in the experiment, like I knew their frequencies that I was looking for, then yeah, I knew where to look for the spikes.
And so then if those spikes weren't where you expected, that meant there's either something wrong with the model or the actual circuit itself?
Yeah, that's these are more like governing equations for the device, I guess would be a way to think about it. I think that, you know, there's definitely, okay, part of the research process is always being like, okay, what are the next steps? You know, like what would we do to take this further? So definitely, if I wanted to look at like more like signals with more complex frequency content. So for example, a brain signal is not just, you know, a 1 kilohertz signal and then whatever my like carrier frequency is. You know, there's going to be all sorts of other frequencies mixed in. Then yeah, that would be like more work to do with the model to be able to look for more like complex frequency content. Does that make sense?
Yeah.
Yeah. So what we did is we have this scenario and we can fit the model very well to this set of experimental data. If we make the experimental data, like the experimental situation, way more complicated, then that would be like a further step.
I don't have another question right now, but I just want to remind the students attending, if you ask questions, you do get more entries in our raffle, so be sure and send those questions in.
Okay, I have a question from Mr. G. For the circuit that our antenna is a part of, what happens when the neural activity is detected? Is it logged somewhere or is it used to trigger something? So this is actually a problem that I think that the brain project is a collaboration between my group, between the group that I'm actually joining in the fall, and another group, and also a big hospital / like Harvard Medical School group. Those are the neuroscientist people that tell us, you know, what to look at, like how big it can be, etc. So we're trying to figure out right now, you know, is the neural activity something that we should be storing locally and then sending back out? Is it something that our equipment is like sensitive enough to detect? And then also, do we have enough power to communicate it back like in real time through a wireless link? And then also with like, you know, brain sensors, it's not just one. You put like thousands of them, hundreds of them all over the brain. And so do I read them all one at a time in a line? Like, do I query them like, you know, sensor A, tell me what you see, sensor B. Is there a way that I can read all of the information at once? So I think that's something that the project team is trying to figure out now.
Hey, Isabel, I have a question for you. So I personally know that you were quite busy in college during your undergrad. And I'm asking on behalf of all the 589ers that are about to go to college or are maybe almost ready to go to college. Do you have any recommendations for work-life balance when it's seemingly all work?
You know, I think that's something that I really had a hard time with in undergrad, and grad school has been way more chill about that, weirdly, than undergrad was. I think a good way to figure out work-life balance is to, you know, really find people that are excited about what they do, you know, in your major and in your classes and stuff, and to also so find like a good supportive group of friends that you can rely on when the works part gets really tough, because that community is something that helped me a lot to get through grad school. And then also, you know, every college has like clubs, or you can get an on-campus job. And so that's a way to find something that's not schoolwork to do that, where you can still have fun. But it's also like perfectly legitimate and good for your mental health if, you know, on Fridays you just want to lay in your bed and like watch Netflix. You know, if that's what makes you feel better at the end of a long week, like you should do it. And I support that. And if you like really need help, you know, talk to your professors and talk to the people in the mental health office and in like the student wellness programs and things. And yeah. Did that sound all right? Cool. Awesome. Okay. Undergrad equals small college, grad school equals big university. Pros and cons of each. Oh yeah. So I went from an 800 person school at Harvey Mudd to like, I think we have like 40,000 people in Northeastern. Not 100% sure. Going to a small school is nice for, you really get to know everybody. You get to know all your professors. You get to know your classmates. Going to a big school, big schools tend to have more resources just because they have more students. When Northeastern also has a graduate program, Harvey Mudd doesn't. And so there's a lot, you know, there's more labs and there's lots more people focused on getting funding for like big research projects, which is just something that like wouldn't have worked at the scale of going to a small school. Do the students have questions? Okay, that's all right. I thought there was a raffle. I mean, like.
There is a raffle. I guess no one really wants extra entries. All right, so while I get the raffle ready, does anyone have any last questions for Isabel?
If you're like too shy to type it into the chat or whatever, you can also, I'm pretty sure my email is, I'll put my email in the chat and you can like email me questions or something. Cool.
Actually, unless you answer this and I missed it, what is your best memory of 589?
What is my best memory of 589? Okay, I mean, every Friday night dinner is probably like my favorite memory, I guess. Like, I think it was very nice to take that time to like form community with 589 by sharing food. But also, you know, it was a great way to ease into learning about what a design review is. You learn about like what everything that's happening on in the different groups on 589, you know, all the subgroups that you aren't involved with. But also like it's a nice low stakes way to like improve your public speaking skills and learning to like talk about the work that you've done. So I think that it's like you know, a nice learning opportunity, but covered in the veneer of like delicious food and like time to chat with your friends. Oh, can I speak about my Dean's List experience? Yeah, you know, it was very nice to have been nominated by 589, and it was like wild and inconceivable that they actually like picked me. That was like crazy, and but it was a really nice opportunity to go on, like come out to the East Coast. I'd never been before. Tour some colleges that I didn't end up going to, and like meet a lot of other really interesting people from other robotics teams. How did I know what frequency I was trying to sense? Is what Mr. Wilton is asking. So in the experiment, we did known frequencies. I was like, I know what frequency the antenna needs to be driven at, and I'm going to make a magnetic field at a certain frequency, and I'm just going to see if I can pick it up. But in an application, you know, if we're trying to make a device that's going to sense low frequency magnetic fields, but I don't happen to know what specific frequency that's going to be at, then I would just, I guess, look for the difference between the spikes. It would be, I could see that being difficult for the rest of the circuit design, actually. But like in like the brain scenario, for example, brain signals tend to have all their frequency content lower than a kilohertz. So I just need to be able to sense up to a kilohertz and then everything that's slower than that. Yeah. So yeah, so actually in that case, on that like weird looking graph, that would just be like everything around the tall spike. So it would be like out to here and then everything in between, which makes its own set of challenges in like designing circuits when you have like very frequencies that are very close together. But yeah. Not an EE question. All good. What are some of the factors that led me to pick Harvey Mudd for undergrad? This is what Adarsh is asking. So CV is a very, very big high school, and Harvey Mudd is a very small school. So when I was applying to schools, I applied to like lots of like UCs and Cal States, but I also looked at some smaller engineering programs like Harvey Mudd. And because I really wanted something that was almost like if 589 became a college, where you like, you know, the mentors, but now they're like your professors, and you know your teammates who are now your classmates really well. And I really liked that Harvey Mudd was going to force me to take a lot of classes that weren't just engineering and like just electrical engineering or just mechanical engineering. You do a lot of science and a lot of math and a lot of chemistry, and then you do a lot of engineering, but you do mechanical engineering and chemical engineering and electrical engineering and all sorts of things. Because I think one of the things that one of the nice things that about 589 is that you like learn that there's lots of ways to solve a problem, and Harvey Mudd is the same way. There's lots of different tools that you could use to solve an engineering problem, and maybe the tools from mechanical engineering are a great way to work on something, but maybe you also need a little bit of like material science knowledge, and you need to know a little bit about circuit design, and you need to know how to like write some code. So I think Mudd is really good at doing that, and so that was why I was like super psyched to go there. Yeah, I have a lot of school pride, so hope that's not like coming across too strongly. But love Harvey Mudd, great place. I think there are like other people on 589 that have gone there like before me and stuff. So we have a decent history of sending people not very far away to Claremont to go to Mudd.
All right, cool. So let's announce the raffle winner. So congrats to Adarsh. You have won the Echo Dot, and I will reach out to you on Discord to figure out how to get that to you. So you'll hear from me soon. Thank you everyone who attended today, and thank you Isabel for talking to us, giving us one of your evenings.
Alexa, turn off little piano. Yeah, Alexa's, woohoo!
Do you have any last words for us?
Feel free to reach out to me if anybody wants to like read my paper or ask questions about electrical engineering. I've gotten the go ahead from my advisor to share it. And if you find, if anybody has questions about Harvey Mudd or about Northeastern or about graduate school or doing research, go ahead and shoot me an email. I'm always happy to chat with 589ers. And thank you all so much for coming, and wear your masks and stay safe.